3-4. 3-4 is about taking everything we've learned so far in 3-2 and 3-3 and ultimately applying it to parallel and perpendicular lines. So let you write that down. I want to make sure this is recording. I don't know what it is. Recording. All right, it is. Shut up. All right, so 3-4, parallel and perpendicular lines. So what we need to be able to do here is eventually define what it means for us to be perpendicular. But as we go through some of this stuff, guys, I want to show you the visual before I give you the theorem. I think just the way I like, I'm not saying this is for you or would be the way you like to see things, but I like to kind of see the relationship that we're talking about or trying to define inside a theorem before we actually see the verbal phrase, because I think it's easier that way. And what I mean by that is, I look at those two lines. Okay, I'm going to tell you that those two lines are parallel. And if we went through and asked for a slope, would you guys agree based off the slope that they are parallel? Okay, and I can move those around here, change the slope, change the position, or whatever to one another. But those two lines are parallel. Okay. What about these two lines? Okay, if I put the slopes on top of those, what would you say about those two? The argument about those two. They are what to one another? Parallel. Okay? So, what about these two? Because those two are A, B, and C, E. So at the beginning we had A, B parallel to DF. We have DF parallel to CE. So we have, in the first relationship, we have these two parallel. In the second relationship, we have these two parallel. The third relationship, I can get from this here, is those two parallel. Does that make sense? So if I take that middleman out, would you guys agree that if these two are parallel and these two are parallel, then the top and bottom ones are parallel as well? Okay, that is absolutely the transitive property. Transitive property with parallelism. Okay? So what we're telling us, or what we're saying here, is if two lines are parallel to the same line, then they are parallel to one another. Okay? And that's what we're seeing there, the idea of the transitive property existing there in the picture there where it says if A is parallel to B and B is parallel to C, then B was that middleman, and we can ultimately say that A is also parallel with C. Okay? That happens all the time. Okay? We see a lot of parallel lines in construction. Look at the tile on the floor, there's parallel lines all over that. Look at the grid on the ceiling, the drop ceiling. There's parallel lines up there, right? Okay? Choose any, because all of those parallel lines on the ceiling are parallel to one another. That means I can pick out any two. Okay? I can pick out the one at the front of the classroom and the one above me right now, and I know for certain they're going to be parallel to one another because of the link between parallelism of all the collective lines in the ceiling. Does that make sense?
What's that one and that one?
Parallel.
What's that one?
Perpendicular. Okay. We'll learn about that here in a little bit though. Okay. So does that make sense to everybody? Okay. You have the transitive property with parallel lines. There at the bottom, you start seeing, just to give you an idea of where to think about this. If you've ever been to Manhattan, okay, New York City, the roads there, and this happens in a lot of cities, but that one predominantly is one maybe jumps to or comes to the top of people's minds a lot of times, because if we were looking at an aerial view of that, you have a bunch of parallel roads. Okay, and what that allows for is like infrastructure to be created in an efficient manner. Infrastructure meaning like water pipes, sewage pipes, telephone lines, data lines for internet and that kind of stuff. It allows that stuff to be distributed and created in an efficient manner. Does anybody ever want to be a civil engineer? You guys know what civil engineers do? They make time out? So civil engineers, they develop roads, they develop plans for city planning. They Yeah, it's infrastructure, but they do that kind of stuff, and one of the properties that they use quite a bit is this idea of the transit property with parallel lines. Okay. All right. Hopefully that's a pretty straightforward concept. Perpendicular lines. Okay. So the rest of our theorems today are going to involve this idea about perpendicular lines. So we need to define what perpendicular means. And perpendicular lines are just lines that intersect to form right angles. That's the definition. Lines that intersect to form right angles. Mathematicians are lazy in regards to writing things, so we don't want to write the word perpendicular out all the time, so we use that upside down capital P as the symbol for perpendicular to. In there we've got two lines, AB and CD. They're perpendicular to one another, so I'd write it as AB perpendicular to CD. And in that picture, you're seeing you get 4 right angles. There are times, guys, where you might not get 4 right angles. You might only get 2 right angles. You might only get 1 right angle, and that's because maybe I'm not using the entire portions of the line. Okay? So as you're writing that down, I'll kind of give you I'll set up a picture here to see what I mean, what I'm talking about. Excuse me? All right. All right, so this is the picture. We have 2 lines intersecting here, right? And there we get 4 right angles, okay? But sometimes, maybe we only get 2 right angles, correct? Does that make sense? Okay? So if they don't pass all the way through each other, we might only get 2. But at the same time, we might only get, see if I can do this right, we might only get something like that, okay, where if I delete, whoa, hide it then. We might only get 1 right angle, just depending on what portions of the line we're using to intersect. Does that make sense to everybody? Okay. For those of you I'll never get 3. Okay, I can only ever get 4 right angles, 2 right angles, or 1 right angle, depending on how our lines intersect. And that's kind of important for us to realize when we start using the definition of perpendicular eventually. Okay. A perpendicular bisector. This is the 3rd time that we've defined this in this course. Okay. So we're on an average of kind of seeing this once every 3 weeks. So my hope is that you kind of take appreciation for that and realize how important this perpendicular bisector term is, and it's going to turn out to be one of our most used concepts once we finish this course. Okay, once we're done, we go back and kind of list the ideas that we talked about and kind of tally the times that we've seen them. Perpendicular bisector is probably going to be at the top of that list. Okay, so I want to make sure we fully understand it. But it's the segment, ray, line, or any essentially any portion of the line that passes through another segment at the other segment's midpoint. That makes it a bisector. But then it's also perpendicular to the other segment, so that's why we get the adjective perpendicular bisector. So just kind of want to show you this relationship. If I look at, see if I can do this. Okay, look at that red segment. Okay, so that red segment just kind of models the infinite number of segments we could ever have. Okay, is that black line going through its midpoint? Yeah. Okay, I don't have the distance on here, but A to C and C to B would be the same length. How many bisectors does that thing have? A lot. What's a better word for a lot? It's going to have an infinite number of bisectors. How many of that infinite? So think about how much infinite is. How many of those are going to be perpendicular to that red segment? Just one. Okay? So every segment has an infinite number of bisectors, but it has one and only one perpendicular bisector. Is that all right? Okay? Now, why is that going to be beneficial for us later on? Is because it's going to help us in regards to that triangle right there. Anybody know what kind of triangle that is? Isosceles. And one of the main features of an isosceles triangle is dependent on that perpendicular bisector. Okay? So that's kind of where this will kind of show up again, maybe the middle of next week, if not the beginning of the following week. Okay? But perpendicular bisector is a very, very important topic for us to describe and talk about. All right, this one here, I want to give you, again, a picture. You guys know you're being recorded, right? Exactly. All right, so would you guys agree that that purple line is perpendicular to the red one? Blue, purple, whatever. It's purple on my screen. All right, so that is perpendicular to the red one, right? That's what 90 degrees tells us. Okay? Well, what if I put in that line right there, okay? And I force that, the way I've created this line is I force it to be perpendicular. Would you guys agree with that? That the black one is perpendicular to the red one. Everybody okay with that? What can you now tell me about the black line and the purple line? Okay? They're parallel. Why? Why? Absolutely. Okay? So they've got these two angles. Those two angles are corresponding, right? Okay? And it doesn't just have to be those, because everywhere up there we've got 90-degree angles, right? We should have 8 90-degree angles there. So we can look at the corresponding, we can look at alternate exterior, alternate exterior, whatever, doesn't matter. But those, if we look at the corresponding one, Stan said if those two are corresponding, they're congruent. Yesterday we had a theorem that said if two lines are cut so that corresponding angles are congruent, then the lines are parallel, right? Okay, so that's what we're getting at here. And why is this nice? Why is this a good feature? Why is this something that we're interested in? Think about this. Look above you. There's a grid up there, right? Okay, so let me, it's a little bit easier for me to draw this on the board, but I want to make sure everybody can see this in the video. Let me do this. Let's say that I've got, so that's the wall to our left right now. Okay, so the door would be down here at A. This is the wall. It's on the smartboard, or has the smartboard. There's the windows. Okay, so looking at kind of an aerial view, so the smartboard is up here, windows are over here, and the door is down here. Right? Is everybody okay with that? All right. If I look above us, okay, we've got this drop ceiling, right? And if we look at the drop ceiling, there's these grid lines on it. Okay, and these grid lines, if you've ever worked with, anybody ever installed a drop ceiling? No. Okay, so we put those metal grid lines in first. Okay, it's kind of a skeleton-looking thing that's just hanging there from support wires. Okay. then we go back through and we put these tiles in, and it kind of makes it rigid. And but there's about a 3-foot gap between the drop ceiling, if I take one of those tiles out, and the actual ceiling of the room. Does that make sense? Okay. And then up in there is like all the wiring and like heating and ventilation ducts and all that kind of stuff. Okay. But when they put that ceiling up, when they put that tile up, they don't do this. They don't go through and say, okay, I'm going to make that rectangle and then come down and make another rectangle and then make another rectangle. Because what's happening if I do that? My rectangles are not going to be what? Yeah, they're not going to be congruent. Okay? Which is, I understand what you mean. So this is how we go about doing this. Okay? We know that maybe those tiles are maybe 2 feet wide. Okay? So they'll come down here and they'll mark 2 feet on that wall. And then they'll mark 2 feet there. And then 2 more feet. And they keep doing that. Does that make sense to everybody? You guys know what a carpenter square is?
Yeah.
Okay, so a carpenter square, those of you that do not know what it is, do a quick Google search here. It's one of these things. Okay? This is called a speed square. Okay? But this is usually what we refer to as a carpenter square. Is that right? Now, the nice thing about both those is that they are manufactured, they're stamped out of sheet metal to be very, very precise, exact 90-degree angles. All right? Okay. So in construction, we use that. We set that up against, let's see here. Set that up against my wall over here. So let me draw a real small version of this. So that would be that square. Does that make sense? Okay. And now I can take that metal piece of my drop ceiling and make sure that it lines up with this edge of my right angle. If it lines up, okay, it's going to come all the way across over here, and then I can attach it to this brace over here. Does that make sense? Okay, or this wall over here. I would probably maybe, just because I'm nitpicky about being right and doing this thing correctly, I would want to come back over here with another speed square or carpenter square and make sure that's a right angle there. Does that make sense? And then I'm going to come down to this one. I'll make sure I got a right angle there. Terrible picture of a right angle. But then put in that bracket or that support. Okay. Do the same thing here. Put my right angle in there. Line everything up. Come down here. Put my right angle in there. Line everything up. Okay. And I can quickly put those kind of horizontal braces of that drop ceiling in. Does that make sense to everybody? Now, what is nice? I never tried to make this red one parallel to the blue one, right? I never focused on that. What I did was I tried to make a right angle here, right? I made these 2 lines perpendicular to the same kind of baseline over here. Does that make sense? And if I can do that, what is then the result? Those things are indeed then parallel. Is that right with everybody? And if I do that all the way through, they're all parallel. And now I've got all those horizontal braces. Now the next thing I would do is come up here, go 4 feet maybe, 4 feet, 4 feet, do the same thing this direction, and now I've created that grid where every one of those rectangles is absolutely the same size, same shape, same size, so they're congruent. And that means then I can put in my tiles and never have one kind of falling out, right? You guys go into some of your rooms, maybe you're in somebody's basement or something like that, you can always kind of see maybe even 1 or 2 tiles that looks kind of off kilter and it's going to fall out, right? There's some classrooms in the high school that are that way. It's because that grid is no longer parallel, okay? And ultimately, with the vertical braces here, if we lose parallelism, we also lose perpendicularity when we start looking at these black lines. So that's one place maybe you can use that theorem. Another place, you guys know what how you do drywalling?
Yeah.
Okay. So drywall, the way we kind of address that is we take, let's use these polygons again. Let me put the grid back in. All right. So in drywall, what we do is we take two 2x4s. Put a 2x4 up top, okay? Put a 2x4 on the bottom. Does anybody know what the 2x4s are called at the top and the bottom of our wall? They're made of wood. Starts with an S. Now those are the vertical ones, and that is not you. So these are referred to, if we were to go home and take drywall off of our walls, okay, and just expose all the stuff that's on the inside, you're going to see the floor is down here, okay? This is where your ceiling would be, okay? These are referred to as sill plates, okay? It is over there, okay? So these are sill plates, and they're just 2x4s laying down on the ground, and they're laying kind of like that on the ground. Does that make sense? Okay. And this one here is then on the ceiling. Okay. But what we do is we mark off and put a 2x4 kind of like right there. Okay. Does that kind of make sense? And now, why are you saying that that's you? That's called a what? That's called a stud. Okay. Then from there, we measure over we go from the center of that stud. We measure over 16 inches, and we put another one. Okay, so put another stud here, another 2x4. Apologize for my crude picture here. We put a stud there, and we do that again. We go 16 more inches from center, come over here, and put another one in. Okay, and now the goal here, guys, and the reason we're doing this and measuring and trying to make sure that this thing is done correctly is because the structure is going to support a lot of weight. Okay. Your walls in your house are supporting the roof, okay? And if you've got 2 stories, then your first floor walls are supporting your second story, along with the weight that is added to by the roof. Does that make sense? So you got a lot of weight on your wall. So we want to make sure that this structure is good. We don't want these things. If I've got one of these studs kind of going like this, okay? We don't have a strong structure now because of the slope or the slant of that 2x4. Okay. When we have perpendicular, we have it's called statics. When you talk about forces that are not moving, so the weight of your building on these 2x4s. With perpendicular objects, those forces are very strong. Okay. A lot of times we refer to forces that are perpendicular as being orthogonal. You ever been to the orthodontist? No. You never been to an orthopedic surgeon? Anybody? Whenever you see the word ortho, they're talking about perpendicular. Okay? Because orthodontist makes your teeth perpendicular to your gums, right? The orthopedic surgeon does skeletal surgeries to keep your body perpendicular to the plane that we walk on, right? Does that make sense? Why don't you? Oh, it's because I don't live in a cave that you and Sister Bear live in. Okay, so when we drywall, okay, why do we want this to be these studs to be parallel? Other than structure, we're going to come through with a piece of drywall, 4x8 piece of we'll call it gypsum. Just a rock. But it's in a sheet form. Okay? So we put it in there. Okay? And now when I put it up against these studs I can't see anymore, right? But I need to attach this to the wall. And so I take a screw and I screw in there, I screw in there, screw in there. Maybe I know that they're up against the floor, so I can screw in all the way down here. But I can't just leave it that way because it's not strong enough. That thing's heavy. It's going to fall off. Okay? So I need to be able to know that when I screw in right there, that I hit a stud. I don't want to screw in right there because then I'm not going to go into anything and that screw is going to come out pretty easily. Does that make sense to everybody? Okay. So how do I verify or determine that I'm absolutely going to hit a stud when I screw in there? Is that I make sure that these studs are parallel to one another. Does that make sense? And the way we do that is we put our carpenter square right here, and we align that first stud to make sure that its side of that piece of wood is lined up against that carpenter square, and it makes a perfect 90-degree angle there, right? and then we do the same thing right here, and it makes another 90-degree angle. And then we can be guaranteed that those two studs are parallel, and we keep doing that down the line, and now all those are going to be parallel. Does that make sense? Okay. There are other ways of doing it, okay, but that is maybe one of the quickest, most efficient ways of doing it. Questions on that? I have punched a hole in drywall. It's not fun. No, it's not, because you don't know where that stud's going to be.
Yeah, I know. I got one.
All right. I haven't punched one on purpose, but I have put my hand through drywall. All right. Just working with it. Let's go to. Is this the next? Yeah. Okay. So this is the last theorem. Okay. This one says, in a plane, if a line is perpendicular to one of two parallel lines, it's perpendicular to both. And I'll go back and let you write that down, but it's this idea. If I have those two red lines are parallel, is that okay with everybody? Guaranteed those are parallel. I'm starting off with that as my if statement. Would you guys agree that that transversal is perpendicular to the bottom one? Okay. The idea then is if these two lines were parallel, should the 90-degree angle and the angle that my cursor is on, shouldn't they be supplementary because they're same side interior if the lines were parallel? So if one of them's 90, what's the other one going to be? 90. And if that's a 90-degree angle where my cursor is, by definition, the black line and the top red one have to be what to one another? Perpendicular. Okay? So we just talked through the proof of that theorem that says if you have two parallel lines, and your transversal is perpendicular to one of them, then it's perpendicular to both of them. Okay? Hopefully that's maybe an obvious statement or obvious idea, but that's going to be a theorem that we use quite a bit. Okay? Now, these two theorems start off as with the phrase in a plane. This one says in a plane. This one says this one doesn't have to be in in 3 dimensions. In a plane, why does that? If I just say if a line is perpendicular to one of two parallel lines and is also perpendicular to the other, that is false if I leave the phrase in a plane out because of this. And I hope it doesn't slow things down for me. But it was slowing down everything at the beginning of class. So this idea here, let me delete all that stuff out. Let's say that I put in that line right there and make a line parallel to it. Would you guys agree that those two are parallel? All right, everybody? Okay. Now, those two are in a plane. But what they're referring to is that all 3 lines, those two and then the transversal that we're going to put in, has to be all in the same plane. Because I could do something like this. Would you guys agree that that line, that vertical line, is perpendicular to one of those parallel lines? But is it perpendicular to both? No. And it's because not all 3 of those lines can be placed inside the same plane. All right? That's why we need that initial statement in a plane. That's not them just putting it in there to be cute. It's eliminating this potential. Okay? Because remember, when an if-then statement is true, there should be no counterexample. Well, if I take the word in a plane out, or the phrase in a plane out, I then open the door for potential counterexamples. This would be one of those. So our phrasing kicks this out. Does that make sense? All right. Just something to think about. That's a good one. Something to say that.